Second lecture on Biot-Savart Law. Today we shall apply the law in few simple cases. Today we shall apply the law to the one-dimensional conductor, for one-dimensional conductor the Biot-Savart law is the magnetic field at a point R due to a current carrying wire is given by R cube, where R is given by the field coordinate R minus the source coordinate R prime. This is the law. Let us consider a current carrying conductor carrying a steady current R. We consider the wire to be along Z axis. We are to find out a field at a point P which is at a distance rho from the wire. So we consider the point P to lie in the xy plane, so that if we consider as per a cylindrical coordinate system, the coordinates of point is rho phi 0. And the position vector is given by R, and this is a current element dr prime which is at this distance. So the R coordinate, the field coordinate is simply OP, and this is in cylindrical coordinate system is given by rho cap times rho, where rho is this distance and rho cap is the unit vector, and the source coordinate R prime is OQ, and since it is along Z direction, it is K cap Z prime. So the relative coordinate R is R minus R prime is equal to rho cap rho minus K cap Z prime. So the magnitude of R is rho square plus Z prime square to the power half, and from here we get dr prime is equal to K dz prime. We use cylindrical coordinate system because if we consider a point at a distance and so rho from the wire, then if we consider a circle of radius rho whose center is on the wire and the plane is perpendicular to the wire, then at each and every point on the circumference of the circle the field will have the same magnitude. That is to say, the problem has a cylindrical symmetry, so use of cylindrical coordinate system will facilitate calculation to a great extent. So with this knowledge we apply the law to find out the field. It is mu 0 I upon 4 pi. Then for dr I write K cap dz prime, K cap dz prime, and for capital R is this. This is a cylindrical coordinate system that has been adopted is a right-handed coordinate system. That means Z cross phi is equal to K, phi cross K is equal rho cross phi is equal to K, phi cap cross K cap, phi cap cross K cap is equal to rho cap, and K cap cross rho cap is equal to phi cap. So this is K cross rho. K cross rho is phi cap. and this will be, since this is this is phi cap, and this is mu 0 I upon 4 pi, and this part is the second term does not contribute because it involves k cap cross k cap. So this is the field. So total field is obtained by integrating this over the conductor. Let us consider the conductor extends from a point from 0, 0 minus ZA to 0, 0 plus ZB, where it is the, so the conductor, if we consider a conductor of finite length, then it extends from, the conductor is AB and this is its coordinates. So the field at point B due to the entire conductor is obtained by integrating this over Z prime. So the result is this is the total field. To evaluate the integration, it is easier to introduce a variable like this: Z prime is equal to rho tan theta, so that dz prime is equal to rho sec square theta d theta, and Z prime square plus rho square to the power of 3 by 2 is equal to rho cube sec cube theta, and the limits are this will so the thing becomes B is equal to phi cap mu 0 I upon 4 pi, and rho is there, and this is rho sec square theta d theta, rho cube sec cube theta, from minus theta a to plus theta b, where this angle is, these are the angles theta a and theta b, these are the angles. So and the integration is cos theta d theta from theta a to theta b. So the result is phi cap mu 0 I by 4 pi rho. The upper limit is sin theta b, and this is sine of mod theta a. This is the field. You see the angle tan theta is Z prime by rho. So this angle is actually theta. This angle is theta. So this is theta b. This full angle is theta b. This is theta b, and this angle is theta a, as they are traced out in opposite sense, so a plus minus sign has been introduced. If we have a conductor of infinite length, then this theta b tends to pi by 2, and theta a also tends to minus pi by 2. So B for an infinite where, B for infinite state where game comes out to be mu 0 I upon 4 pi rho. This is 1, this is 1, so comes 2, so the result is 5 cap mu 0 I by 2 pi rho. This is the result for an infinite where. And if we have a finite where, then this is the point of observation, then the field at this point will be, this is the distance rho, this is the upper angle of theta b, and this is theta a. These are the quantities involved in the evaluation of the field. You see, the field is directed along the phi cap. That is, if we consider a cylinder whose axis is the current carrying conductor, then at each and every point the field is along the phi cap. That is, the field is the tangential on the surface of the sphere, which is very much evident from this vector notation. So this completes the calculation of field due to a straight wire using Biot-Savart law. For finite wire, this is the expression for the total field, and for infinite straight wire, this is the expression for field. Now we come to the second problem. We consider a current carrying conductor in the form of a circle of radius a and carrying a steady current I. Our objective is to find the field at the center of the coil. So the problem is like this. We have a circle carrying a current I. The circle is placed in a, we assume the center of the circle as the origin of the coordinate system, and the circle lies in xy plane. So z-axis is the axis of the circle. Our aim is, and this is the center. If we consider a point between this on the circle, then at any point on the circle, the position vector of the source point is a rho prime cap. Here again we use cylindrical coordinate system due to the symmetry of the problem. So a is the radius of the circle and rho prime is the radius vector. So dr prime is equal to a phi prime cap d phi prime. And if we consider for field at center, for field at O, we have r is equal to a null vector. So that capital R is equal to r minus r prime is equal to minus a rho prime cap, and the magnitude of R is simply A. So the field at O is equal to mu 0 I upon 4 pi dr prime cross R by R cube. This becomes mu 0 I upon 4 pi. For dr prime I write this one, cross. For R it is minus a rho prime cap by a cube. Now there are a and there is a cube, so this gets cancelled. Mu 0 I upon 4 pi a, and then the minus sign and the vector is phi cap cross rho cap by rho cap times d phi. This is equal to minus k cap. So this adjusts the sign and this result is plus k cap mu 0 I upon 4 pi a d phi prime, and the total field is obtained by integrating it over the angle phi. So and the total field is obtained by B at O is simply k cap mu 0 I upon 4 pi a into this integration gives you 2 pi, so this is k cap mu 0 I upon 2a. This is the field at the center. The field is directed in this direction if the field at the center is directed along the axis. Now if we consider field at an axial point P, then this is the field coordinate r and this is the relative coordinate of the field point, and the field point has obviously coordinate 0, 0, z. So if we consider the field at P, then the only thing changes is that this is k cap z and the corresponding quantities will change accordingly. So field at an axial point, this is an axial point, field at an axial point. So in this case we have r is equal to r minus r prime is equal to so the magnitude of r is a square plus z square to the power 3 by 2. The field is field at P is equal to mu 0 I upon 4 pi for dr prime cross r by r cube. This I write mu 0 I upon 4 pi for dr prime I write a phi prime cap d phi prime cross r. For r it is now this simplifies to mu 0 I a by 4 pi a square plus z square to the power 3 by 2, and the rest of the quantity is this phi cap cross k cap. This is rho prime cap times z. This is when this crossed with this, and when this is crossed with this is minus k, and this minus sign makes it plus. Since in cylindrical coordinate system k prime is a fixed direction, so one need not to put k prime. Now overall this is phi prime. So we see that if we calculate field, if we consider this element, the field will have two components. This is the field, it will have two components, one along this direction, another along this direction. If we consider a diametrically opposite point, the field will have, these are the components. So these are the five row components of the field which are opposite for two current elements situated diametrically or at diametrically opposite positions. So these two cancels out and the field along the longitudinal direction adds up. So to say, this is the longitudinal component of field and this is the transverse component of field. On integration, this transverse component gets cancelled. This is the physical reason how we come to the result. But here we consider that rho prime is I cap cos phi prime plus j cap sin phi prime. In the entire result there is no phi dependence except in the rho prime cap. When we integrate it over d phi prime from in a complete range 0 to 2 phi, so this gives you 0. So rho prime cap d phi prime complete integration 0, and this part contributes to 2 pi. So the total field at point P, total field at point P is equal to mu 0 I A upon 4 pi a square plus z square to the power 3 by 2. Then here we come a 2 pi a k cap. So on simplification the field becomes k cap mu 0 I a square, mu 0 I a square Now the field is always, if the current flows in the anti-clockwise sense, which is taken to be the positive sense for any circulating quantity, then the current is always directed along the positive direction, no matter whether the point lies above the plane or below the plane. That is the field. All along the z-axis, the field is directed along positive z-axis, and the field, the direction of the field changes only when the circulation, the sense of circulation is changed. That is when the current flows in clockwise sense, then the field at positive z-axis or on negative z-axis, both are directed along the negative z direction. Now come to the variation of the field. If we see that the field is a maximum at z is equal to 0 at the center of this center, and the magnitude is simply this goes to for z is equal to the 0, this is a cube. So this is what we obtained for the field at O, and for other points we see the field is symmetric about z-axis. That is, if we replace z by minus z, since z appears as z square, the field is symmetric, so it is maximum. This is BP and this is z. This is the origin. The field has at large, this is symmetric, and at large distance you can ignore A in comparison of z, and this large distance it varies as minus z cube. So asymptotically the field varies as 1 by z cube. The third option would be to find out the field at a general point which is not on the axis of the circle. The calculation of the field using Biot-Savart law in such a non-axial point becomes very difficult, and we keep it aside for the time being. And after introducing the concept of magnetic dipole, we shall take up the calculation for the field due to a circular conductor at an off-axial point. Now we shall apply this law to to a practical application which is known as Helmholtz double coil galvanometer. The theory will require this expression, so we just keep the expression. So Vp is equal to mu 0 I s square to s square plus z square to the power 3 by 2. This is the field. We shall apply this to a case known as Helmholtz double coil galvanometer. For the galvanometer is an instrument which is used to measure current. Helmholtz double coil galvanometer is specially designed for the accurate calculation of a small amount of current. A magnetic needle is placed between two circular coils, two identical circular coils, and whose planes are we have two circular coils, coil 1 and coil 2, each having radius A, and carrying current I in the same direction, same sense, and they are separated by a distance 2d. This is coil 1, this is coil 2, and this is the midpoint O. Between the centers, it is the midpoint O, and we are to find out the field at a point P. In actual Helmholtz double coil galvanometer, what one does, we place a magnetic needle at this point, and it will be as we have seen in the case of electrostatics, that when an electric dipole is placed in an electric field, it experiences a pure torque when the field is uniform, and in non-uniform field it experiences a torque as well as a translatory force. The magnetic needle is generally used on a pivots. This is a pivot, and the needle is allowed to move along this direction. If a translational force acts on this, then this axis, this vertical axis will be tilted, and there will be some restriction to the free movement of the needle. So for the free movement of the needle, one should have no translatory force on the needle. That is, the needle must be placed in an uniform field. So our objective is to find out the field at P where this distance is z. Since the current flows in the same sense through both the coils, the field at P is just the sum of the individual fields, because due to this coil the field is towards the right, and for this coil the field is also towards the right. So the field at Z will be some constant k times this distance. This much is d and this distance is z, so this is and the constant k is this constant mu 0 I s square 2 pi s, and this factor has been taken care of there. And to increase the magnitude of field, there are n turns. If there are n turns in each of the coils, then this is the constant. Our aim is to find out the field. The aim is to adjust these two so that the field becomes uniform. So to this end we calculate dB dz, which is from this we will have d plus z minus 5/2, and from there we will have minus sign because of this. And the second derivative we shall also calculate the second derivative of b. You see that this term first and this part has been differentiated keeping this constant, and when this part is differentiated the result is 5 d plus z whole square and now come to the differentiation of this part. This gives you simply this minus minus makes it plus, and for this term you will have again for the field to be uniform, for this part has to be 0. So if we put dB dz is equal to 0, then this expression has to be 0. The obvious solution is z is equal to 0. So it is found that the field is uniform, or the first derivative of the field is 0 right at the center because it is the point of symmetry. And if we put d2b dz2 is equal to 0 at z is equal to 0, because we use this, then we find that with z is equal to 0 we get these two terms, and these two terms becomes identical with z is equal to 0. So we need not to consider both those two terms together, simply this entire thing will be multiplied by 2. So the result is a square plus d square to the power minus 5/2, because this becomes a square plus d square with z is equal to 0, and this is minus 4 d square upon a square plus d square to the power minus 7/2 is equal to 0. Or if we take this in the denominator, a square plus d square to the power 7/2, the result is a square plus d square minus 5d square is equal to 0. That is a square minus 4d square upon a square plus d square by 7/2 is equal to 0. That is, this part has to be 0. the, that is to say, for the second derivative of the field to be 0, this gives you a square is equal to 4d square, or 2d, the separation of the coil, separation between the coil is equal to the radius. That is, if we have two coils of identical coils of radius a, when they are separated by a distance 2d, the first derivative of the field will be 0 right at the midpoint, and to make the second derivative 0, we have to place the coils such that their separation 2d is equal to a, equal to the radius. Then the second derivative of the field will also be 0. If we go on calculating the third derivative, it is found that with this value, with z is equal to 0 and a is equal to 2d, the third derivative also vanishes. So this also leads to this also leads to the 0 value. So if we expand the field B as a function of Z in Taylor series, what we get? We expand the field B as in Taylor series, so it is B at 0 plus del B del Z at Z is equal to 0 times Z plus del 2B del Z2 at Z is equal to 0 times Z square by factorial 2 plus still higher order terms this is the, if we apply, if Z is equal to 0 and A is equal to 2D, then this is 0, this is 0, this is 0. So the field becomes B0 plus some constant times Z to the power 4 plus still higher order terms with Z nearly equal to 0 and A is equal to 2D. So the field, for small values of Z, the field can be considered to be constant B0 field. This is the theory of Helmholtz double coil galvanometer. Another way of arriving at the result is that if we have second derivative of the field is, first and second derivative of the field is 0, so this leaves you B is equal to B as a function of Z, AZ plus B with dB dZ is equal to A is equal to 0. So the field is only a constant part B. This is a second order theory, and this considers even higher order theory. So we see that if we want to find a field which is uniform over a region, one must have the first derivative as well as the second derivative of the field to be 0. In that case, the field distribution becomes like this. You have a coil, first coil, second coil, this is the coil 2 and this is the coil 1. The field variation is like this. So the resultant field between these two will be the sum of these sum of this, and the field will be something like that. Sorry, here it should match with this one here. And in this region the field may have a downward trend if the separation is very large. It will have, in this region the field may be, if D is high, it will have this type of variation if D is low, and for an optimal value of D the result will be this. It will remain constant over a large separation. This is the condition that A is equal to 2D, and this is the case when the separation is greater. 2D is greater than A, and this is 2D is less than A. So this is the theory of Helmholtz double coil galvanometer, and it allows the needle, since the needle is placed in an uniform magnetic field, pure torque acts on the needle and no foul occurs due to the touching of the vertical axis of the pivot with its rims. So it enables one to very accurate calculation of magnetic field current using Helmholtz double coil galvanometer.